Okay, so in chapter 5, you guys all have protractors and stuff, or compasses anyway, but chapter 5 has a very specific focus. And we're going to be looking at specific relationships that exist within triangles themselves. So chapter 5, our overall focus for the next 5 sections will be relationships in triangles. Relationships in triangles. Not like love triangles, drama type stuff that seems like it's a episode for, I don't know, some soap opera or something. But we're going to be looking at these. Now, today, we're going to start 5.1. And in 5.1, we're going to be looking at 2 different things. I'm going to write it on the board first in shorthand. I want to see if you guys recall what it means. I'll write the real words here in just a second. Any idea what I've said? So these are bisectors. I agree. And I'll actually write it out, but I just want to make sure like this is the shorthand that we'll use. What does this symbol mean? Perpendicular, which just means right angles. Perpendicular. And instead of writing perpendicular bisectors and whatever, I'm just going to write it here. Perpendicular and what is angle? That's a weird one. Angle bisectors. Okay. This is what we're after. Now, because we're going to be dealing with both of them, it's pretty natural that we'll split it up over 2 days. And we're going to jump right in with our first topic. And here in a moment, you'll be doing your bell ringer part of this. We are going to start today with perpendicular bisectors. Now, can we all agree with this notation? Does anybody hate the notation? Okay, I don't know if I believe you, but I'm cool with that. Let's talk about perpendicular bisectors. And here's the very first thing that I want you to do. I want you guys on your page, and this is like the bell ringer part, if we need to have one crossed out because you didn't do it right the first time, I'm okay with it. Here's what I want you to have so that we can talk about. You're going to draw a segment. I don't care how long it is, and we're going to call it AB. And what I want you to do is I want you to construct a perpendicular bisector. Now, right off the bat, perpendicular meaning what? So real quickly, and one more time. 90 degrees. So Ray, I'm going to put you on the spot for a second, but not in a bad way, I hope. Ray's only in here for a semester. I don't know if you guys have noticed this, but what percentage of questions is Ray answering? Roughly, would you guys guess? Maybe somewhere in there. Do you guys agree that he's willing to give a lot of answers? I'm cool with that. Like, doesn't bother me. When Ray's not here, who's going to give 70% of the answers then? If it's not Lily. It's not me. I'm going to start, if I have to, we're going to calculate through way more than we have been. Not in a bad way, but like, it's okay to be wrong. Don't be scared of being wrong. I think a lot of you guys will probably be wrong a lot of the time. That's okay. We learn from it. Be okay with it. Perpendicular means 90 degrees. Now, we did this earlier in the year. It's been a while. Anybody remember how we did it? Okay, well, 2 minutes, try to figure it out, and then I'm going to pull up GeoGebra, and I'll look at it on mine, and we'll see it there. See if we can get a perpendicular bisector. Cool. I'll give you a moment. So here's my wonderful perpendicular bisector. B as in Bacter, just for the record. Cool. We all good with that? Now, if I were hypothetically to go ahead and make a triangle, and I'm just going to put any point up here, and we'll call that point C. Notice I put point C on the what? What is that dash line that we just drew? It is so this is the midpoint, I agree, but this whole thing is more than just a midpoint. It's a perpendicular and a what? Not a bisector, sorry. This is my perpendicular bisector, like right there. Now, as we look at this, couple things that we want to make sense of with this. If I draw this, and here's my point C, what kind of triangle do I have here? So I have how many triangles, I guess, first? I see 3. Left, right, and big. You guys agree with that? Okay. Now, if I look at just the big triangle first, are there any segments you guarantee are the same? So AM and MB. Why? And we're going to write out the justifications here, just so we can see them. AM is congruent to MB. I agree with you. Good. That means it's bisected. They're both half. Okay. Does everybody agree that those must be the same? Anything else that's the same? And maybe we'll look at these two triangles. Between these two triangles, anything that's the same about those two? CM? Why? Okay, and somebody other than Lily or Ray, CM is congruent to CM because it's congruent to itself. What's the name of that property? Good. The reflexive property. Okay, so I'm going to just put some dashes there too. Now, it's been a while, not really that long. Are the two triangles AMC and BMC, are they going to be congruent to each other? Is this triangle congruent to this triangle is the question at hand. Can you give me a reason? Let me make it not rhetorical. Why are they the same? There's one more thing that we know is the same on both these triangles. 90 degrees. Is this congruent to this? So do you guys agree that triangle AMC is congruent to triangle BMC? And what's my reasoning? And I'm going to put the right angle there as well. Why? Don't talk back. SAS. Now you could use leg as well, but this is really side angle side. Okay. Now the whole reason that we're talking about this is you don't even realize it, but we pretty much just proved a theorem. Now, in the end, if these are the same, we know that AC and BC are also the same. Do you guys agree with it? Would it have mattered, and you don't need to write this one, but if I had put point C down here instead, or if we say there's D, is AD also going to be congruent to DB? And it's for the exact same reason, right? Side angle side, we still get the same relationship. What we have just done is worked out a much better definition of perpendicular bisector, and you may not even be aware of it yet, and that's awesome and fine. Instead of just saying it's 90 degrees and it cuts it in half, we get something bigger out of this deal. So we're going to define this a little bit further, and it's actually going to take the form of a theorem. So our first theorem in chapter 5 already. And just so you guys know, these theorems, I'm going to number them, but they do 5.1 and 5.2 right here with this idea. I'm going to write it as an if and only if and just combine it into a single theorem. Okay, so we'll call this theorem 5.1, and then the next theorem that we write down will be 5.3 because I'm just going to include the converse as well. So theorem 5.1 is exactly our perpendicular bisector theorem. Okay, now any single point that I put on here, is it going to be the same distance from A and B? No matter where I put it. It could be here, it could be all the way down here if it's still there, but those would still be the same length, right? They have to be. What that tells us is that according to this theorem, and we just proved it before we wrote the theorem down, what we can say is the following. A point, and it doesn't matter which point, we're going to say a point is on the perpendicular bisector of a segment if and only if which just means both directions, right? So if a point is anywhere on this bisector, then what did we conclude is its relationship about the endpoints? So its distance from the endpoints is equal, right? And there's a better way that we can say that, but I agree with your statement of congruent. We're going to say a point is on the perpendicular bisector of a segment if and only if it is, and we're going to add a new word, and I think we'll be okay if we just stink it in here. If I just write equi, what do you think I'm going to, like, what does that mean, just as a root word? Equivalent or equal. Are we okay with that? So we're going to say a point is on the perpendicular bisector of a segment if and only if it is equidistant from the endpoints. Now, again, I just want to stress, we just proved this before we even wrote the theorem. If you give me some segment like this, and you give me the perpendicular bisector, no matter where I put the point, it's going to form two congruent triangles, and I'm always going to get these segments being the same, meaning they're the same distance from the endpoints every single time. Do I need to give a more formal definition for equidistant, or can all agree that it's just equal distance? Excellent. All right, I need to not ask just yes questions because that's the worst type. Cool. Does it seem super hard to do? All right, let's get some problems done. Okay, today is going to be super chilled. It said this is supposed to be 2 days, but I don't see how we make it 2 days. We'll see. All right, we're going to do an example. And we're going to use perpendicular bisectors. All right. I don't know how to make apostrophes look nice. Commas also, for that matter. All right, we're going to use a little bit of editing magic here. We're going with this wonderful picture. What I want you guys to help me do, and we'll do this as a whole class, and I will use the calculator, is I want to find on this problem the length of segment PL, and in the process, I want us to justify it. Now, it's not a proof. We're going to have proofy looking stuff, but it's not given show. I just want to make sure we can start seeing like how this theorem applies. So we are trying to find PL, just this little length right here, and we're trying to justify it along the way. Now, my guess is that everybody in here can probably answer this question. If you don't see it yet, that's okay. I'm going to give you like 45 seconds, and we'll do a hard 45 seconds. Talk with your neighbors, see if we can't see the logic through the problem, and then we'll formalize it together and make sure that we're justifying everything. Cool. 45 seconds. Chat with your neighbors. I'm going to call randomly. The justifying part's a little bit harder. Carson immediately, and I was picking on him about it. So if anybody else was having the same thing, you just kind of lucked out that I didn't call on you. Carson claims that Kn is a perpendicular bisector. Now, maybe. All I know for now is that it's perpendicular, right? Why do we think or know that this is a bisector? And I'm going to write each of these things down. Kn is a perpendicular bisector. Why? All we've marked is that it's perpendicular. Well, okay. Well, this is on a line. That's not a perpendicular bisector. Or maybe you look at that and say, well, it's not perpendicular. Okay, well, this is perpendicular. Is that a perpendicular bisector? Like, and I'm being snarky with it, right? Like, intentionally. Why do I think, and why did you think that it is a bisector? And let's see here. I don't care if the answer is right or wrong, but I just care about an answer. Will it turn on? Ooh, they're low, but we'll get it. There's 8 of you and 1 of me. You know what? I'll be number 9. We'll go crazy with it. Gosh dang it. Number 9. Well, I just saw a theorem a second ago that said it's on the perpendicular bisector if and only if it is equidistant from the endpoints, right? Notice JK is the same distance as LK, which are both endpoints. We see that K, which is on Kn, is equidistant from the endpoints. Do you guys agree with that? These are the same, and that's true if and only if this is a perpendicular bisector. So this is the exact theorem that we just wrote. And I'm just going to justify this, and it's not quite proofy, but we'll just say, hey, check it out. JK is equal to KL, and that's our theorem that we just wrote. Okay, as soon as I know that this is a perpendicular bisector, immediately the logic starts flowing. That means that JN is the exact same length as what? Number 2. What's the same length as JN? I don't know who number 2 is. NL. Do you agree with this statement, Andrew? Why?
Because they're both not the same triangle.
So I'm okay with that. Better language would be the fact that we bisected, because this segment was bisected and this is the perpendicular bisector. But yeah, I agree with that. Okay, so that now we know that this is 14 right here. So we'll just say implies that NL equals 14. Now, again, you guys can get to the answer much quicker than this, but more than just the simple mathematics, I care about the logic that we're building to get in here, because when we expand to bigger, harder problems, the same logic will apply and it won't be quite as obvious. Now that I know that NL is 14, I need to be able to make a claim about MP. Number 5, Mike Papa. Can you tell me anything about this segment? Why? Why do you think this is a bisector? Love it. Raylene, notice that NM and ML are the same distance from these endpoints N and L, which means that MP is a perpendicular bisector. We are told it's perpendicular. I'm cool with that. Mike Papa is perpendicular bisector, and we'll use the shorthand. Of what? And that can be open to anybody. So careful. What am I bisecting perpendicularly? N L. This, and I think your logic was probably fine, but the language was wonky. This is the perpendicular bisector right here of this segment. As soon as we get there, and I know that P then is the midpoint, or that this is a perpendicular bisector, PL is simply how much of NL. This is how much of this whole distance right here. Half. And Carson, you're right. We then conclude that PL equals 7. And we're there. And again, I think that if you made a bunch of assumptions without justifying, you're going to get the right answer, obviously. But it's certainly possible and not terribly hard to do exactly this and make it look like it is and try to trick you without having the justification. Be okay with the logic here. One more really quick. Am I going too fast, too slow? Do-si-do, here we go. Bro. Okay, sorry, bruh. Okay, I want you guys to do one. Much easier problem. Maybe. I want us to find the value of x for the following triangle. And I did not measure carefully, so I'm just going to go to here, and I'm going to go to right there, so it's nice. Nope. Nope. Every time. There we go. Look at that. Okay. I'm going to add this vertical line and just like that. The fact that that is marked with a square angle mark and dashes on each of those means that guaranteed that vertical line that I've just drawn, or segment rather, is the what of this? More words. One more word. It's the perpendicular bisector. Okay, so here's the fun part. I'm told that this side right here is x squared minus 2x. And I'm told that this is 3. I want you guys to find x. Cool. I'm going to give you a moment. Okay, now at this point, I'm trying to embed a little bit of these algebra ideas that we've spent a little bit of time. If it's x squared, it gets uglier, right? Like if it's just x by itself, it's an easy-ish problem typically, but x squared is bigger. What do we have to or get to use if we have to have something with an x squared? What's our F word, Vincent? Factor. Now, when we factor things, I want it equal to what on one side of the equation? 0. So I'm going to subtract 3 immediately. Drew, if you've not done this, you should. I'm going to subtract 3. You should subtract 3. And here it is. To solve this, how do we go about it? In here, we only have 2 shortcuts, right? We have GCF, we have grouping. Those are the only things that we've done. There's nothing that goes into all 3 of these. So what do I do? So how do I group it? So a 1 times a -3 is a -3. I now need 2 numbers that multiply to be -3, but they add up to what? So they have to multiply to be -3, and I'm going to make this note. Multiply to equal -3, but they have to do something else at the same time. They have to add to equal -2 because it's this number. Okay, well, let's figure those out. 2 numbers that multiply to be -3 but add up to -2. If I do 1 and -3, or -3 and 1, however you want to write it, do these multiply to be -3? Do they add up to -2? Hey, we're golden. Now, can't remember because I did this with all my classes. Did we talk about the significance of this 1? I think so. Ashley, can you remind me the significance of that 1? And that's okay. Did we really talk about it in here? We must have. If this is a 1, there's a shortcut. I'm simply going to have an x, and then what's one of my 2 numbers? -3. And I'm going to have an x, and what's my other magic number? +1. Now, we still have equals 0. And I don't recall if we ever did the actual equals 0 part or if we just did the factoring. But check this out. If I say, hey, 2 things multiply to be 0, does one of them at least have to be 0? If I say 2 things multiply to be 0, one of them must be 0. Is that true? I think so, because Vincent, give me any number out of infinity. Okay. When I multiply that by my number, I get a 0. What's my number? And Lily, it looks like I'm looking at you, but I'm looking at Vincent. He just happens to be right over your head. You're fine. 67 times my number is 0. What's my number? Has to be, right? There's no other option. It can't be 5 or 2. Like, oh, only 0. So here's what we have to do. Here's this number times this number is 0. What value of x makes this number 0? Or, if we want to see all the work, what do we get when we solve this? X equals 3. That seems reasonable. What do we get if we do this one? -1. So x plus 1 equals 0 is my other option. Now we get x equals -1. Now, in either situation, do they work? Like, you're going to be tempted to say this one doesn't work, but we can check it. Let's try 3 first. If I do 3, what's 3 squared?
9.
Minus, what's 2 times 3? And 9 minus 6 is? So this one just worked, and we just checked it. That was fine. X could be 3 in this situation. Let's try -1 also. If I take -1 and I square it, what do I get? Minus a -2. So I would have, and I'll write this one out, -1 squared minus 2 times -1 is what we're trying to plug in, right? This is a 1. What happens when you minus 2 multiplies by -1? Does this one also give us a 3? So this one also works, which means for our problem, if the value of x is all we're asked to do, what value or values did we just find? X equals, what's the first option that worked? Or 1. -1, thank you. And we're done. Now, your book will never make you factor them, but I will in class. Now, didn't even really feel like we were using the theorem other than the fact that it was marked as the same, but the same thing still applies, and we get a little bit of factoring algebra review. All right, let me see, because I have a note on the assignment. We are going to play democracy. Oh, I'm in the wrong section. Okay, for democracy, you guys get to choose. We have 15 minutes right now. Do you want to have the remainder of class 15 minutes to work through a few problems first, or do you just want to keep going and have tomorrow be like all homework? Let's just do the first one. That way it's split up so that it's not just all lecture today and all lecture tomorrow. Cool. You guys get 14 wonderful minutes in class to work through the following problems. If you finish early, this is not a threat, but if you finish early, we'll get a head start on tomorrow's stuff, and we'll just have a little bit more time tomorrow in class for homework. So here we go. For tonight, let's see. Hey, we're in a new chapter. What just happened? Don't like that. For tonight, it is 12/1. Happy December. That was lesson 5.1.1, not lesson. And I'll put all the other stuff here in a second, but we'll just go to the homework first. Homework! You get homework 5.1, which you will find waiting for you lovingly on page 211. And then these are going to be in a weird order, but I want you to do 14 first so you don't have to take a compass home. 14, 8, 16, and 17. Okay, full disclosure. I'm going to add problems to this tomorrow, just so you're aware. I will not take this assignment tomorrow, but what I will do is I will take the total assignment for all of 5.1 on Wednesday, which means theoretically you should just do these 4 right now. Start with number 14, and I'll leave you to it.